Hi everyone, I'm Fangyu from the University of British Columbia. This is a joint work with Ali, Jianyu, Chen, Evan, who are also from UBC, and Duan from Chilean Technology. Our project called Bamboo is open source and website is down below. Our work is to study the performance of Chained-BFT, which is the new variant of Byzantine fault tolerance state machine replication in the era of blockchain. Let me briefly talk about why we should care about BFT SMR in the first place. First, it is because of the cryptocurrency hype. Since the inception of Bitcoin, the cryptocurrency cap has soared past $1 trillion. As we know, cryptocurrencies or blockchains are essentially BFT SMR, which replicate service state for Byzantine fault tolerance. The second reason is that enterprise blockchains have been emerging rapidly, and there are plenty of innovative uses coming out for blockchain beyond financial services. Many big players such as JP Morgan, Microsoft, and Facebook also joined the game and have been developing their own blockchain services. Now, let's talk about how BFT SMR evolves. The most renowned BFT SMR is PBFT from 1999. In a happy path, a request has to go through two voting phases, prepare and commit, before being replied back to the client. You may have noticed that each voting phase incurs quadratic message complexity, and even more during a view change. A recent work called Hot Stuff from 2019, 2 decades after PBFT, brings up the Chained-BFT paradigm and achieves linearity and responsiveness. It achieves the goal by introducing another voting phase. Given that the overall message complexity is linear, there's no significant difference between normal path and view changes. Therefore, the leader can be changed after each proposal for better decentralization without imposing any overhead. Hot Stuff also makes use of the chain structure from blockchain to pipeline the protocol. For example, the quorum for the prepare phase of the proposal from leader 3 also serves as the quorum for the pre-commit phase of the proposal from leader 2, which can further be seen as the quorum for the commit phase of the proposal from leader 1. Now we can conclude that Chained-BFT is characterized by its chain structure, the proposed vote scheme, and a set of simple rules for safety and liveness, which we call safety rules. Due to the difference of safety rules, a family of Chained-BFT protocol have been proposed, and many projects has been using them in their blockchain architectures. We observe that this new family of protocols have subtle difference in design choices, which could cause significant impact on performance. But there's no study to show and explain the variance. So in this work, we tend to answer the question, how do cBFT protocols vary in performance? Our approach is based on the previous observation that cBFT protocols share so many similarities. So to fairly compare their performance, we need to abstract the key differences and implement shared components. This observation leads us to build Bamboo, which is prototype and benchmark framework. By using Bamboo, you can quickly prototype a cBFT protocol and benchmark it under various settings. Moreover, to validate our implementation and dissect their performance, we also build a performance model using current theory. Our model is in turn helps us forecast the performance of a cBFT protocol without even implementing it. The design rationale behind Bamboo is to first abstract the set of safety rules. These rules are applied in different phases of a protocol, which are proposing rule, voting rule, commit rule, and state update rule. We provide fine design interfaces for the safety rules and let developers implement them. To enable apple-to-apple comparison across different protocols, we also provide implementations for the rest of the components that are shared across different protocols, such as networking, pacemaker, blockchain data structure, and benchmarker. We also observe that cBFT protocols are subject to performance attacks, such as forking attack and silence attack. The design of safety rules can determine the tolerance to the performance attack. So we also use Bamboo to study the impact of the attack on different cBFT protocols. Even though these attacks cannot violate liveness and safety guarantees, they can still impose significant impact on performance. Take the forking attack, for example. The proposer of block 4 deliberately ignores block 2 and block 3 and builds block 4 following block 1, thus overriding block 2 and block 3. Note that it is difficult to identify this type of attack since no one can distinguish whether the forking is due to network asynchrony or malicious behavior. To better capture the impact of the performance attacks, we introduced 2 additional metrics besides throughput and latency. They are chain growth rate and block intervals. Chain growth rate is defined as the rate of committed blocks appended onto the blockchain, while block intervals measure the average number of views a block takes from being added to the blockchain until being committed. We implemented hot stuff, two-chain hot stuff, and Streamlit using Bamboo and have done comprehensive evaluations on them. The reason we choose the 3 is because they are good examples to show the trade-offs of cBFT's design choices. On the left is the figure for protocols under forking attack with 32 fixed nodes. The number of Byzantine nodes vary from 0 to 10. 2 insights we can get from this figure are, although Streamlit has the worst performance, this is due to the cubic message complexity. It is more tolerant to forking because of the voting broadcasting. Also, hot stuff is more sensitive to forking because it needs 3 consecutive blocks with quorums to commit 1 block, whereas the others only need 2. For more juicy results, please see our paper. Here we summarize our contribution. We proposed a prototype and benchmarking framework for Chained-BFT called Bamboo. We implemented 3 representative cBFT protocols and conducted comprehensive evaluations using Bamboo and obtained many insightful results. We built a mathematical model for cBFT protocols to dissect their performance and validate our implementations. If you want to build your own blockchain in less than 300 lines of code, please come to the project's website. That's all. Thank you for listening.